All right, hello. So, I am Tasneem, and we are students from Evan Hardy Collegiate here in Saskatoon. This is the 8th year that Evan Hardy has been part of the students on the Beamline program. However, we are all brand new members ranging from grade 10 to grade 12. And thank you so much for having us here, and we hope you enjoy our presentation.
Hello, I'm Huey. Since September, we have been working with some of the CLS staff and other scientists to develop a method to extract toxin from the environment. We call this project Waste Can Remove Waste, Extraction Potential of the Proprietary Polymer.
Hi, my name is Melody, and we came across this idea for a project after reading an article describing mercury removal using a polymer synthesized from orange peels and sulfur. We decided to research this further as this article was only recently published. Fortunately, we were able to contact the author of this article, Dr. Justin Chalker of Flinders University from Adelaide, Australia. Luckily, Dr. Chalker replied in response to our request for collaboration, and he was interested in the students on the Beamlines program and was eager to help us. Through Dr. Chalker, we had access to a sulfur limonene polysulfide polymer, as well as a new patent-pending polysulfide rubber made from elemental sulfur and a renewable alkene crosslinker derived from plant sources.
Hi, I'm Jax. So the polymer were designed with high sulfur content to bind with metal pollutants such as mercury. Keeping this in mind, and we also wanted to examine to see if there is any other toxic material this polymer could bond with. Then we choose selenium because selenium forms a strong bond with sulfur as well, and hopefully this will have the future ability to be used in our environment to help clean up the mining waste.
So I'm Kayla. We also chose to continue working with mercury chloride and the polymers because the product of the bond between these two were still unknown. So as you can see here, in Dr. Chalker's research, he tested many different substances on the polysulfide polymer, but only mercury had a color change. And he observed that in the patent-pending polymer as well. We wanted to use the Synchrotron to help us determine what elements may be involved in this bond and the potential speciation of these elements. Dr. Chalker prepared solutions of 100 millimolar mercury chloride bonded with the limonene polysulfide polymer as well as the patent-pending polymer and shipped them to us for our research.
We decided to work with selenium, a toxic substance that had the ability to bind with sulfur. Selenium is relevant to Saskatchewan because sodium selenite and sodium selenate both act as contaminants in Canada's environment due to the continuous uranium and coal mining situations that are happening. A dosage of 55 micrograms of selenium is the daily needed intake to maintain our bodies for teens and adults. However, once this amount is increased and it is taken excessively, it can act as a toxic substance to our bodies and the environment. And due to all these health risks and these environmental risks and its ability to bind with sulfur, we decided to work with this product.
Hi, I'm Ramisa, and I'll be talking about the procedure. So we started off by using 0.6 gram portions of the proprietary polymer, and we placed it in a diluted solution of both sodium selenate and both sodium selenite. We then proceeded by leaving this in the solution for 24 hours. After the 24 hours were up, we removed the polymer and we scraped the surface of it. After we did that, we used a mortar and a pestle to crush and grind it into smaller pieces. When we were done using that, we placed them into sample holders and used them in the beam lines.
So during our beam time at the CLS, we are given access to the BioXAS and Ideas Beamline. The BioXAS Beamline is used to conduct research with life and environmental sciences, and that was the beamline that we used to analyze all of our mercury samples. The Ideas Beamline, however, is used for industry work and educational purposes, and that was the beamline that we used to analyze all of our selenium samples. But both of these beamlines work in a very similar way. So it begins with a strong electron beam entering the beamline, and then the first detector, I0, will measure the intensity of this beam. The beam will continue on and hit the sample, where it can then be fluoresced, which is measured by a detector, or it can go through, measured by another detector. And together, these three detectors will help us determine different data about our sample.
Hi, my name is Jay. X-ray fluorescence, or XRF, are a general test to inform us the existence of a certain element in a sample. One test usually takes at least 2 to 3 minutes to finish. So basically, X-ray fluorescence has a K-shell that contains electrons. And outside of that K-shell has another L shell. And it also contains electrons. When our sample is irradiated by a high energy of photon, one of the electrons from the K-shell will then be removed or ejected. However, one of the electrons from the L shell will then fill that up. So when the fluorescence is released, the fluorescence will hit the new electron from the K-shell and then fluoresce it, which determines all the different types of elements that can be found in that sample. And as you can see in this graph, we have the green line here, which represents our controlled polymer. And we found out that it contains sulfur, argon, and iron. Then afterwards, we also ran controlled air, or the environment for the black line. And we found out that it contains argon and iron. And this determines us that sulfur can only be found in the controlled polymer.
SAINS is another scan that looks at a more in-depth at the specific energy absorption and the detail. It tells us the specific speciation within our element that was being researched. It takes between minutes to several hours depending on the amount of detail that it's conducting. And then it presents us a graph of the energy and absorption, but the range can be determined in small specific ranges. It has an absorption near an edge structure, which will help us determine how it corresponds with the edge structure and the electrons within our specific element. This can vary depending on the chemical environment of our element. Understanding the characteristics of the edge structure will help us determine also the oxidation state. So as you can see on the left there, we have our L edge, which would determine all the different mercury samples that are being tested. And on the right here, we have our K edge, which determined all of the selenium samples.
So hello everyone, my name's Christina. So now here you are looking at final XRF graph for our selenium sample. As Jay said before, argon, iron, and sulfur are already present before the experiment. And after the experiment, our selenite sample, as you can see the red graph here, it has a huge selenium peak at the end of the graph. So we're suggesting that there might be a reaction between our selenite sample and the patent pending polymer.
My name is Peter, and I'm going to work through the analyzation process of our selenium for zinc, and it's specifically said to be selenate. So as you can see here, we're going to take a look at the bottom two lines. The orange one is selenium sulfide standard, and the blue line is selenium oxide standard. They all rise and form a peak. somewhere before our standard forms a peak. So that can tell us that the compound formed in our polymer might not be those two standard. Then we're going to take a closer look at selenate 10 millimole and selenate standard, which is the gray line, because that can, in an overlap graph, that tells them more information. As you can see here, the blue line is selenate 10 millimole standard, and the orange line is selenate the blue line is selenate 10